a boiler explosion. We'll look at what causes boilers to explode and the steps you can take to avoid this dangerous situation. Next, we'll look at a problem that can lead to a boiler explosion, the loss of flame in the furnace. Finally, we'll consider less serious situations, such as the loss of boiler auxiliaries, tube leaks, boiler overpressure, and equipment fires. Now, while these abnormal operating conditions are usually not life-threatening, an operator must keep in mind that a small problem can quickly become a large problem if not treated properly. As we progress through this program, you need to keep in mind that the procedures we'll demonstrate are typical of how many plants handle abnormal and emergency conditions. Your plant's procedures will give you specific information on how you should respond. Now, the chances are extremely good that if you follow your plant's operating procedures and monitor your equipment properly, your boiler is not going to explode. However, by understanding why boilers explode and the situations that have the potential for causing explosions, you're better prepared to anticipate the possibility of an explosion and act to keep that explosion from occurring. In general, boiler explosions occur when an abnormally high concentration of combustibles is suddenly and uncontrollably ignited inside the boiler. Now, there are a number of situations that can lead to a high concentration of combustibles in the boiler furnace. Startup is one example. As you know from earlier training, fuel, air, heat, and a chemical reaction are the four basic requirements for combustion. As this simplified diagram of a burner port illustrates, in preparation for startup, an operator first sparks igniters to provide the heat source to start the combustion process. The operator next establishes secondary airflow to the burner to provide the air requirement. With the igniter sparking and air supplied for combustion, the final step is the introduction of fuel to the burner. The fuel and air combine to form a combustible mixture. The heat from the igniter starts the combustion process. Now, that's the way it's supposed to work. However, boiler explosions occur during unusual conditions. Let's suppose that the igniter malfunctions and does not spark as it is supposed to. We'll use the same illustration to see how an explosion might occur. The operator turns the controller to start the igniter sparking. However, in this case, the igniter is slow to respond and doesn't spark right away. The operator next establishes airflow to the burner port and then starts fuel flow. The igniter still doesn't spark. The air and fuel form a combustible mixture. The mixture accumulates in the boiler as more fuel and air are supplied. If the igniter suddenly begins sparking, it will ignite this abnormally large mixture. The result is an explosion. The same thing can happen if a combustible mixture is present in the boiler prior to startup, and an operator sparks igniters without first purging the boiler. An operator can easily avoid these situations by carefully following plant procedures and purging the boiler before sparking igniters. Then, verifying that the igniters are operating properly before introducing air and fuel to the boiler. Explosive fuel mixtures can also occur during normal operation. If either the flow of air or the flow of fuel to the burner port is temporarily interrupted and then reestablished, an explosion may occur. Again, from earlier training, you know that if one of the four basic requirements for combustion is eliminated, combustion will cease. If you have established a proper boiler flame and airflow and fuel flow are properly matched, your burners will operate the way they're supposed to. However, if airflow, for example, is interrupted, one of the basic requirements for combustion is eliminated. This will cause the boiler flame to go out. Unless the fuel flow is immediately stopped and the boiler is purged, an abnormally high concentration of fuel may accumulate near the burner port. If airflow is subsequently reestablished, this large concentration of fuel can ignite suddenly and cause an explosion. Interrupting fuel flow will also extinguish the boiler flame, and unless steps are taken to correct the problem according to procedures, an explosion may result when fuel flow is restored. Generally, an operator has several indications that make it possible to verify that a flame is present in the boiler. Viewing ports, mirrors, and television monitors allow visual indication that combustion is taking place. Typically, if an operator discovers that the boiler flame has gone out, procedures indicate to immediately shut off the fuel supply and to purge the boiler for a designated amount of time before restarting the flame. Another situation that can lead to a boiler explosion is difficult to detect and may cause an explosion with no warning whatsoever. To give you one example of how this unusual situation might occur, we'll use a boiler that has a gas bypass system for steam temperature control. As you learned earlier, under normal conditions, flue gas flows from the furnace area over the superheaters and reheater in this section of the boiler, over the economizer, and then through the air preheaters. In a boiler with a flue gas bypass, if the outlet temperature of the superheated steam gets too high, this damper is opened, which redirects a portion of the flue gas away from the superheaters. When superheated temperature returns to normal, the damper is closed and flue gas flow proceeds normally. Gas bypass systems usually do not require the use of fans. Flue gas can be redirected simply by opening a damper. The reason's simple. The pressure in this part of the boiler is higher than the pressure in this part, and fluids naturally flow from an area of higher pressure to an area of lower pressure. When the damper is closed, a dead spot may occur in the ductwork at the entrance to the gas bypass system. A dead spot is an area where little or no flow takes place. Now, let us suppose that, for whatever reason, the boiler flame was momentarily lost and an abnormally large quantity of fuel entered the boiler. The operator responded properly by cutting fuel flow to the burners and increasing airflow to purge the boiler of all combustibles. But let us also suppose that a portion of the combustibles accumulated in this dead spot around the gas bypass damper and were not purged from the boiler. When purging was complete, the operator followed the proper procedures for reestablishing the boiler flame. But remember, combustibles remained in this dead spot in the ductwork. The boiler continues operating for some time with nothing unusual happening. However, let's suppose further that the operator needs to adjust superheater outlet temperature and opens the bypass damper. The combustibles that have accumulated in the ductwork are no longer in a dead spot. They are immediately reintroduced into the flow path of flue gas going to the economizer, or, due to some back pressure around the damper, are forced back into the furnace area of the boiler. The result could be sudden and uncontrolled combustion. In other words, an explosion in either the furnace area, the ductwork, or near the economizer. Now, what we've just done is a lot of supposing, but let me stress that boiler explosions occur under uncommon conditions. If it is possible to make up a situation where an explosion could possibly happen, it is also possible that under rare and unusual circumstances, those conditions can exist and cause an explosion. Let me again stress that boiler explosions are uncommon occurrences. By following your plant's operating procedures, the chances of them happening to you are extremely slim. What you can do to keep explosive situations from developing is to carefully monitor your boiler flame and to make sure that combustion is taking place properly. You should also keep a careful watch on the fuel flow and airflow to the burners to make certain that both are being supplied in proper proportions. Finally, since the boiler explosions, which have occurred in the past, have often been fostered by a loss of boiler flame, knowing the procedures for dealing with this situation and the proper procedures for purging your boiler will prevent boiler explosions. In the next part of this program, we'll look at some situations that can lead to the loss of a boiler flame and the typical procedures for returning the boiler to normal operation. For now, read over the material in your text on the cause of boiler explosions and answer the questions. If you need any help with this material, ask your instructor before going on. In a coal-fired plant, a bright yellowish-orange flame in the furnace is a positive indication that combustion is taking place properly. Anything that jeopardizes the combustion process jeopardizes the flame and also jeopardizes the safety of the people in the plant and the plant's ability to produce electricity. If the boiler flame goes out, you have only seconds to respond. In many cases, procedures will indicate that the first steps in dealing with a loss of flame are shutting off all fuel flow to the boiler and either maintaining or increasing airflow to purge the boiler of all combustibles. Unless action is taken immediately, the boiler could explode. When we discussed boiler explosions, we touched on some of the situations that can lead to a loss of flame. In this part of the program, we want to look at some other situations that have the potential for causing a loss of flame. What you can do to avoid a loss of flame. The indications available to you to verify whether the boiler is functioning normally or if a loss of flame has occurred, and the action necessary for keeping the boiler under control. There are a number of operating conditions that are common to a plant that have the potential for causing a loss of flame. One example is wet or frozen coal. During wet weather, rain or snow can increase the overall moisture content of coal. In addition to creating handling problems such as freezing and sticking, wet coal is difficult to dry and pulverize. In some cases, this condition can cause blockage in coal pipes, interrupting the flow of fuel to the burners. An alert operator should recognize operating conditions where there is a potential for a loss of flame and take appropriate action to minimize the chances of it occurring. In some cases, this action may require increasing the flow rate or temperature of primary air going to the pulverizer. In other cases, additional igniters or a warm-up burner may be used to ensure proper combustion. Another situation that can cause a boiler flame to go out has to do with the way burners are arranged to support combustion. As this simplified diagram illustrates, burners are usually positioned one above the other. When operating normally, the flames from the burners converge near the center of the furnace. With this arrangement, the flame from each burner helps support combustion on other burners. Here, for example, the bottom burner helps support combustion of fuel from the middle burner, and the middle burner helps support combustion of fuel from both the top and bottom burners. If fuel flow to one burner is interrupted and the flame goes out, it may cause a loss of flame from other burners. In this example, if the middle burner flames out, it can't help support combustion on the top burner or the bottom burner. The result may be that the top burner and bottom burner also go out. In situations where coal is difficult to burn, lighting off igniters or warm-up burners can be used to assist the combustion process. Using additional igniters or warm-up burners is a typical approach to avoiding a loss of flame, especially when there is a potential for the flow of fuel to be interrupted. Now, there are other situations that can lead to a loss of flame that the operator will not be able to anticipate. A typical example is a boiler tube rupture. Boiler tubes are subjected to both the intense heat of the furnace and the high pressure of the boiler. On occasion, a tube may rupture, blowing water and steam into the furnace, superheater, or economizer section of the boiler. Depending on the location of the rupture, it may endanger the boiler flame. Ruptures in the furnace area of the boiler are usually the most critical. Ruptures in the area of the secondary superheater may also cause a flameout, while a rupture in the area of the primary superheater and economizer will not usually upset the boiler flame. When a boiler tube ruptures, water or steam is released into the boiler under high pressure. If the rupture occurs in the furnace area, it may extinguish the boiler flame. Since tube ruptures usually occur without warning, an operator must be constantly ready to shut off all fuel flow to the burners and purge the boiler of combustibles. Since a tube rupture can cause a loss of flame, an operator needs to know how to verify that there is a boiler flame. Let's go on to look at the indication that an operator uses to verify a loss of flame. An operator in a control room usually has a number of ways to visually verify that there is a flame in the furnace. A television monitor is one example. This monitor is used to observe the boiler flame from the control room and to verify that there is either a flame in the boiler or that a loss of flame has occurred. Mirrors located just outside the control room may also be used to verify that a flame is or is not present in the boiler. Mirrors are usually aligned to allow an operator to see a reflection of the boiler flame through observation windows in the boiler. Of course, the most reliable indication of a boiler flame comes from opening an observation door and actually looking inside the furnace. However, if a loss of flame is suspected, you should not attempt to open an inspection door. If a flameout has taken place, opening an inspection door could cause enough of a draft to ignite the combustibles in the boiler and cause an explosion. If you must make a visual inspection to verify a loss of flame, use the inspection windows near the burners. While television monitors, mirrors, and inspection windows allow an operator to actually see inside the boiler, none of these indications is totally foolproof. Mechanical or electronic problems with either the monitor or the television camera in the boiler may give a false indication of a loss of flame. Mirrors used to monitor the boiler flame may from time to time get knocked out of alignment, rendering a false indication. Observation windows near the burners may be blocked by ash or slag, also giving a false indication. Now, the chances of all these indications being false at the same time is very slim. Therefore, it is important to check all available indications when verifying a loss of flame. In addition to visual indications, control room instrumentation can be used to check for a loss of flame. If the boiler flame goes out, steam pressure and temperature will drop. The main steam recorder in the control room will indicate the drop in temperature. A flameout will also upset the flow of air and gas through the boiler, sometimes making balanced draft boilers go positive or pressurized boilers go negative. An operator can monitor this on pressure gauges in the control room. One thing that you need to keep in mind, however, is that a loss of flame is not the only condition that can cause some of these changes. Also, it may take some time for these changes to be indicated on control room instrumentation. In most cases, it is best to use visual indication as the primary means of verifying a loss of flame. As an operator, your best safeguard against a loss of flame is to follow your plant's procedures and carefully monitor control room instrumentation to make certain that all systems are operating properly. You should also make sure that television monitors, mirrors, and observation windows are available and indicating properly. Finally, if you suspect that there is a potential for problems with a reliable fuel or airflow. Additional igniters or warm-up burners should be used according to procedure. In the event that unusual conditions cause a loss of flame, you need to be able to respond according to your plant's procedures. As we've indicated throughout this program, most procedures will require that at the moment a loss of flame has been verified, fuel flow to the boiler is shut off. And depending on procedures, airflow is either maintained or increased to purge the boiler of all combustibles. Procedures will indicate how long the boiler must be purged and the airflow required to ensure safe conditions. Once fuel flow has been stopped and the boiler purged, most procedures will require the operator to return the boiler to normal operation as rapidly as circumstances will allow. This is to prevent steam pressure from dropping low enough to trip the turbine. Now, in the event that the prevailing conditions make it impossible to return the boiler to normal operation, then the operator must take the appropriate action to trip the turbine. Once the loss of flame has been dealt with properly, the operator should notify supervisory personnel and the load dispatcher. Keeping everyone that depends on your unit for the production of electricity informed will ensure that the supply of electricity to your customers will not be interrupted. In a little while, we'll look at abnormal conditions that may arise from the loss or malfunction of boiler auxiliaries. For now, though, read over the material in your text on the loss of boiler flame and answer the questions. If you want more information on dealing with the loss of flame in your plant, ask your instructor to help you before going on. A loss of boiler flame or a boiler explosion are unusual conditions that threaten the safety and well-being of the plant and the people working in it. Fortunately, these situations are rare occurrences and can usually be avoided by following plant procedures. Not so rare, however, are problems with auxiliary systems. To operate properly, a boiler requires the use of a number of auxiliary systems and components to keep it supplied with fuel, air, and water, to circulate water and steam, and to remove the products of combustion. Boiler auxiliaries are generally mechanical devices that will occasionally malfunction and fail. If this happens, the operator must identify the problem, take appropriate action to stabilize the boiler, and return the boiler to normal operation as quickly as prevailing conditions allow. In this part of the program, we're going to look at how an operator deals with the loss of boiler auxiliaries. The equipment that we'll cover includes induced draft and forced draft fans, air preheaters, boiler water circulating pumps, and boiler feed pumps. In general, the auxiliaries that we've mentioned are arranged in pairs, such as these boiler water circulating pumps. Each component in the pair is capable of handling at least 50% of the normal load. To ensure that a reliable supply of steam is available for the production of electricity, an operator must know the capacity of the unit when everything is operating properly and its capacity if one or more of the auxiliaries fail. An operator must also know how to recognize and identify the failed component and the proper procedures for stabilizing the unit and returning it to normal or reduced load operation. We'll begin this part of the program by looking at the loss of FD and ID fans. Forced draft fans supply air to the boiler under a positive pressure. On a balanced draft boiler, like the one shown here, induced draft fans are also used to draw air and flue gas through the boiler, keeping the furnace under a slight negative pressure. Both FD and ID fans are motor-driven. If these motors fail, the fans won't work. Likewise, if the damper controller or other fan components break, the operator may lose the ability to control the flow of air through the boiler or to remove the products of combustion. Both of these situations can eventually lead to a loss of flame. There are a number of indications that can alert an operator to problems with the FD and ID fans. If the drive motor is the source of the trouble, the amp meter indicator on the control panel will show a loss of motor amps, and the draft gauges will indicate a decrease in the boiler pressure. If the problem is associated with the damper controller, the operator will not be able to control air or gas flow through the boiler. This will also be indicated on draft gauges. If something inside the fan is broken, the operator will usually be able to hear a clanking or rubbing noise coming from the fan. In addition to these indications, annunciator alarms may also sound to help the operator identify the source of the fan problem. If one fan fails, the operator must take appropriate action to stabilize the unit. For example, on a balanced draft boiler, the loss of one of the ID fans will tend to make the furnace go positive. This is because the forced draft fans are pushing air into the boiler at a greater rate than the remaining induced draft fan can draw air out of the boiler. Under these conditions, the boiler can continue to operate if the load on the unit is reduced. Most procedures will require that the operator isolate the defective fan and immediately reduce the flow rate of fuel and air to rates which can be handled by one ID fan. This means that steam flow, feed water flow, and condensate flow must also be reduced. Once the load on the unit has been reduced and stabilized, the operator should immediately inform the shift supervisor and load dispatcher. If conditions allow, the operator should then try to return the unit to normal operation. On rare occasions, the operator may lose both FD or ID fans. When this happens, the operator has little or no control over the flow of air and gas through the boiler. In this situation, the boiler cannot continue to operate. Most boilers have interlock systems that will automatically cut off fuel flow to the boiler and extinguish the boiler flame if both FD or ID fans are lost. If this is the case, the operator must immediately follow plant procedures for purging the boiler of all combustibles. If a fan cannot be returned to normal operation quickly, then the operator may also have to trip the turbine. Similar action is required to deal with the loss of air preheaters. Most boilers have two air preheaters which are used to increase the temperature of combustion air before directing it to the boiler. The symptoms of air preheater failure include a decrease in the air temperature, leaving the air preheater, and an increase in the flue gas temperature, leaving the boiler. In coal burning plants, the loss of an air preheater may make it impossible for the pulverizers to dry and grind the coal. However, it may be possible to continue to operate the boiler at a reduced load. If both air preheaters fail, the boiler will have to be shut down immediately. In our discussion of FD and ID fans and air preheaters, all the fans and preheaters had to be operating for the unit to operate at full load. The loss of one of the components leaves the operator with an either-or situation. Either reduce load and continue operating, or shut down the unit. In the case of boiler water circulating pumps or boiler feed pumps, the situation may be different. As this illustration of boiler water circulating pump shows, there may be an extra pump available for backup purposes. Backup or redundant pumps can be put into service in the event that one of the other pumps malfunctions. If your plant has redundant pumps, then in the event of a loss of boiler water circulating pump or a boiler feed pump, starting the appropriate redundant pump will usually solve the problem. However, if your unit does not have redundant pumps and a pump fails, you're back to an either-or situation. Depending on the severity of the problem, an operator either reduces the load on the boiler or shuts the unit down. The loss of a boiler water circulating pump will affect the circulation of water and steam through the boiler. This will be indicated in the control room by both annunciator alarms and a change in the differential pressure between the inlet and outlet headers of the pumps. The loss of a boiler feed pump will cause a sudden drop in feed water flow and drum level. If all the boiler water circulating pumps or boiler feed pumps fail and can't be restarted, the boiler must be shut down and the turbine tripped. The thing to remember about the loss of a boiler auxiliary is that in most cases, you can continue to operate at a reduced load. Your job is to identify the problem, isolate the failed component if possible, and take immediate action to stabilize the boiler. In most cases, this means that you can reduce the load on the unit so that you can continue to operate. You then take whatever action is necessary to return the unit to normal operation as quickly as procedures and circumstances will allow. Take some time now to read over the material in your text on the loss of boiler auxiliaries and answer the questions. Ask your instructor to help you if you have any problems. Boilers differ in many ways, but what they all have in common are miles and miles of boiler tubes, piping, and ductwork to carry various solids and liquids into, out of, or through the boiler. Now, with all of this equipment for conveying solids and liquids, it's a pretty safe bet that somewhere along the line, a leak will occur. In this part of the program, we're going to look at three types of leaks that are associated with boilers. They are leaks that occur inside the boiler, leaks that occur outside the boiler, and leaks that occur through the boiler casing. As you know, the inside of a boiler consists primarily of tubes. Water and steam flow through these tubes under high temperature and pressure. Every so often, the temperature and pressure takes its toll and causes a leak inside the boiler. For our purposes, we're going to divide leaks that occur inside the boiler into two categories, tube leaks and tube ruptures. The difference between the two is the quantity of water or steam released inside the boiler and the severity of the problems they cause. A tube leak is a small break in a boiler tube that allows a relatively small quantity of water or steam to escape. A tube rupture is a large break that allows a much greater quantity of water or steam to escape. A rupture can have a significant effect on the water level in the boiler drum and can directly affect the operation of the boiler. As you've learned, ruptures also have the potential for extinguishing the boiler flame. A boiler tube leak can occur anywhere there's a boiler tube. An operator usually has a number of ways of knowing that a tube is leaking. During a boiler inspection, for example, the operator may hear a hissing sound coming from the boiler in the area of the leaking tube. Depending on the location of the leak, an operator may be able to see the leaking tube when making a boiler flame observation. Instrumentation in the control room may also tell the operator that a tube is leaking. A difference in feed water flow to the boiler and steam flow leaving the boiler is one indication of a leak. Another is an increase in the makeup rate for the boiler as indicated by this pen on this recorder. In most cases, a leaking boiler tube does not significantly affect a boiler's ability to circulate water or steam. However, a tube leak is an abnormal operating condition and has the potential of damaging the boiler if not carefully monitored. When a tube leak occurs, hot water or steam is released from the tube under very high pressure. If the leaking water or steam comes in contact with other boiler tubes, it can cut through those tubes and cause other leaks. If an operator isn't careful, a small leak can snowball into a major problem. A tube leak can also affect a boiler's ability to handle fly ash. Dry fly ash moves out of a boiler along with the air and flue gas on the way to the stack. Between the boiler and the stack, a fly ash handling system separates the fly ash from the flue gas. However, if steam or water from a leaking tube is sprayed into the gas flow path, it will turn the dry, powdery ash into mud, causing it to stick to boiler tubes. The wet fly ash will insulate the boiler tubes and prevent efficient heat transfer, or it may clog the air preheater. Wet fly ash will also stick inside ash hoppers in the fly ash handling system. If the problem is severe enough, the boiler will have to be shut down and the ash hoppers opened up and cleaned. While the problems we've just mentioned can affect the operation of a boiler, in most cases a tube leak does not require an immediate shutdown. A tube rupture, by contrast, often does. A tube rupture can be caused by metal fatigue or result from a small leak that suddenly increases in magnitude. When a boiler tube ruptures, a large quantity of water or steam is released inside the boiler. This usually results in an immediate decrease in boiler drum level. Depending on the location of the rupture, a loss of flame can also occur. Tube ruptures generally occur suddenly and without warning. An operator must be ready to take immediate action. For the most part, a tube rupture requires an immediate shutdown of the boiler. This means the operator must shut off fuel flow and purge the boiler of all combustibles. Then, follow plant procedures for shutting down the boiler, tripping the turbine, and informing supervisory personnel and the load dispatcher. Of course, the inside of a boiler is not the only place that a leak can occur. Piping and ductwork that supply the boiler with the various liquids and solids necessary for normal operation can also leak. Any point where pipes are joined together or are connected to equipment or valves have the potential for developing leaks. The action that an operator must take to correct the problem will vary depending on the size, location, and severity of the leak. For example, most boiler drums have gauge glasses like this that can be used to check the water level in the drum. Due to the tremendous pressures and temperatures that a gauge glass is subjected to, leaks may develop. In most cases, the amount of water that leaks out of a gauge glass does not affect the operation of the boiler. The operator may choose to live with the leak until the boiler is taken offline for scheduled maintenance, or the operator may isolate the gauge glass by closing shut-off valves on either side of it. Once isolated, maintenance can be performed on the gauge glass while the boiler continues to operate. Once in a great while, a gauge glass may blow, spraying water and steam around the area of the boiler drum. This situation could endanger the safety of the people in the plant and the operator's ability to maintain proper drum level. The operator in this case has three choices of action to take. If it is possible to get to the isolation valves, the gauge glass can be taken out of service and repaired. However, if the leak is severe enough, the escaping steam may make it unsafe for personnel to attempt to isolate the gauge glass. If this is the case, the operator may be able to maintain the proper level in the boiler drum by increasing the make-up water rate. The boiler can then continue operating until it is convenient to schedule a shutdown. This being the case, the operator must isolate the area around the leaking gauge glass and inform supervisory personnel of this abnormal condition and the need to schedule the unit offline. If neither of these choices are possible, then the operator must take the unit offline immediately. Regardless of whether a boiler leak occurs inside the boiler or outside the boiler, the operator must make a decision as to the appropriate action to take. In most cases, the choice of action will involve isolating the leak and continuing to operate until maintenance can be scheduled. Or, if the leak is severe enough or endangers the boiler flame, shutting the boiler down. Once in a great while, a leak will develop in the boiler casing. The severity of the leak and the design of the boiler will determine the action taken by the operator. Balanced draft boilers, for example, operate under a slight negative pressure. For the most part, any leak in the casing will draw air into the boiler. Air leaking into the boiler through the casing can affect the combustion process, the operator's ability to maintain a proper boiler flame. If this is not the case, however, the operator can continue to operate the boiler until a shutdown can be scheduled. If combustion conditions cannot be properly maintained, the unit must be taken out of service immediately. Pressurized furnace boilers, on the other hand, present an operator with a different problem. Pressurized furnace boilers operate under a slight positive pressure. This means that a leak in the boiler casing may allow flame or hot gas to get out of the boiler. Flames extending outside the boiler casing can cause fires and create a safety problem for plant personnel. In most cases, a leak in a pressurized furnace boiler requires an immediate shutdown. In this part of the program, we've concentrated on problems associated with boiler leaks. We've looked at tube leaks and ruptures, which occur inside a boiler, leaks in equipment and components, which generally occur outside the boiler, and leaks that occur through the boiler casing. For the most part, an operator has two choices for dealing with boiler leaks. If possible, the operator should isolate the leaking component and continue operating until the unit can be scheduled offline for maintenance. If the leak is severe enough to jeopardize the boiler flame or the operation of the plant, then the unit must be shut down immediately. In both cases, the operator must decide on the course of action and inform supervisory personnel and the load dispatcher according to plant procedures. Take some time now to read over this material in your text and answer the questions on boiler leaks. If you want additional information about the procedures used in your plant, ask your instructor to help you before going on. A boiler operates at specific temperatures and pressures. Unless the temperature of the steam is hot enough and its pressure high enough, the turbine cannot operate properly. Under certain unusual operating conditions, the pressure in the boiler may exceed the designated value for normal operation. If this happens, tubes in the superheaters and reheater may rupture, and in extreme cases, the boiler drum may rupture. To protect the boiler from overpressure, a special type of valve is installed in the superheater and reheater outlet lines and on the boiler drum on drum-type boilers. These special valves are called safety valves, and they protect the boiler from overpressure. Safety valves come in a number of shapes and sizes. Regardless of whether a safety valve is installed on a boiler drum or on a superheater or reheater, essentially safety valves all work the same way. This is what a typical safety valve looks like. The basic components that make up a safety valve include a housing, a manual release lever, a spring, a disc, a seat, and both an inlet and outlet line. During normal operation, the spring holds the valve disc securely against the valve seat in the closed position. Pressure from the component where the valve is installed is exerted against a small portion of the valve disc at the inlet. As long as the pressure exerted against the valve remains within the designated value for the component, the spring will hold the valve in the closed position. If, however, the pressure at the valve inlet increases and exceeds the designated value, the increased pressure will push the disc off its seat. When this happens, pressure is exerted across a larger area of the disc, causing the valve to rapidly move to the open position. This is known as a safety valve lift or popping a safety valve. When a safety valve lifts, pressure is released through the outlet line, which is usually vented to atmosphere. Most safety valves are designed to close automatically. In order for a safety valve to automatically close, the pressure in the component must drop to a value below the popping pressure. For example, this safety valve is set to lift when pressure exerted at the inlet exceeds 2,000 psi. To close automatically, the pressure in the component must drop below 1,800 psi. Now that you have a basic understanding of how safety valves work, Let's look at how they are used to protect the boiler from overpressure. As you learned earlier, the superheaters and reheaters in a boiler are designed to carry superheated steam at designated pressures and temperatures. The flow of steam through superheater and reheater tubes is important for a number of reasons. Steam flow is necessary to drive the turbine generator, to cause an efficient transfer of heat from the flue gas to the steam, and to keep the superheater and reheater tubes cool by removing heat from the tubes. If steam flow is stopped, the turbine generator can't operate. Also, unless an alternative flow path for the steam is provided, pressure and temperature inside the superheater and reheater tubes will increase, causing them to overheat, rupture, or even melt. To protect superheater and reheater tubes from overpressure and to provide an alternative flow path for steam, safety valves are installed in outlet lines of superheaters and reheaters. If steam flow to the turbine generator is cut off, the resulting increase in pressure will cause the safety valve to lift. This, in turn, will provide a flow path for steam, protecting the tubes from overheating. On drum-type boilers, safety valves are also installed on the steam drum. Safety valves on the steam drum lift if the pressure in the boiler exceeds designated values. This can happen when there is a decrease in steam flow without a proportionate decrease in fuel and airflow. If the demand for steam decreases, yet at the same time the boiler is being supplied with fuel and air at a rate greater than demand, the temperatures and pressure inside the boiler may exceed appropriate values for normal operation. In this case, safety valves on the steam drum may lift to relieve this pressure. There are usually a number of indications to alert the operator to overpressure in the boiler. Control room instrumentation will indicate increased pressure at the superheater outlet and increased pressure in the boiler drum on drum-type boilers. In addition to these indications, annunciator alarms will also sound to make the operator aware of the problem. Safety valves are necessary to protect the boiler from damage. However, they sometimes cause an operator some problems. The common problem associated with safety valves is leaks. As we've said, once pressure is reduced by the safety valve, the valve will automatically close. However, the valve seat or disc can be damaged when a safety valve lifts. If this happens, the disc will not seat properly and the valve may leak. An operator approaches a leaking safety valve in much the same way as any other leak in the plant. The operator must determine if the leak is severe enough to disrupt the operation of the boiler. If it is, then the operator has little choice but to shut the boiler down according to procedures. If, however, the leak is minor and the unit can continue to operate, then the operator must carefully monitor the safety valve to make sure the leak does not become worse and schedule the boiler out of service for maintenance. Take some time now to read over the material in your text on safety valves and boiler overpressure. And when you're finished, answer the questions at the end of this part of the text. If you have any questions concerning boiler overpressure, ask your instructor to help you before going on. In this last part of the program, we're going to look at problems that are primarily confined to coal-burning plants. These are equipment fires. From your knowledge of fuels and combustion, you know that under certain conditions, coal can ignite by itself. This phenomenon is referred to as spontaneous combustion and is a frequent problem in the coal yard. We'll use this simplified drawing of a coal pile to review how spontaneous combustion occurs. Coal in the coal yard is subjected to the heat of the sun and the heat produced by decaying organic matter in the coal. In some cases, the heat is sufficient to start combustion in a small section of the coal pile. Air pockets in the pile, as well as the air in the surrounding atmosphere, keeps the combustion process going. Coal pile fires are generally slow, smoldering fires that don't produce much in the way of flames. As a rule, coal yard fires do not endanger plant operation. In general, coal pile fires are put out by compacting the coal with bulldozers. Compacting eliminates air from the combustion process, and the fire smothers. If coal pile fires are not extinguished, the fire can be transferred from the pile to the coal bunkers, feeders, and pulverizers. How an operator handles fires in the bunkers, the feeders, or the pulverizer will depend on the severity of the fire and the circumstances and conditions in the plant. Let's look at bunker fires first. Bunker fires can be caused by an existing fire in a coal pile being transferred to the bunker when coal is moved to the plant. Bunkers can also catch fire due to spontaneous combustion. An operator can often detect a bunker fire by the smell of burning coal, or in some cases by smoke rising out of the burning area of the bunker. A bunker fire does not usually interrupt the operation of a plant. In some cases, an operator may decide to leave the fire alone in hopes of its burning itself out. In most cases, however, the typical procedure for dealing with a bunker fire is to burn the bunker empty. What this means is that the operator uses the coal stored in the burning bunker as rapidly as possible, and that the bunker is emptied of all coal before it is refilled. Usually, as the coal flows through the bunker, the shifting of the coal compacts it and removes air spaces. This removes one of the requirements for combustion and may extinguish the fire. However, when an operator decides to burn the bunker empty, it's done with the understanding that the fire may be transferred from the bunker to the feeders and to the pulverizers. We'll look at feeder fires next. In most cases, a feeder doesn't catch fire all by itself. Feeder fires usually result from burning coal being transferred to the feeder from the bunker. Symptoms of a feeder fire include smoke coming from the feeder and hot metal surfaces. As with bunker fires, the most common action taken by an operator to handle feeder fires is to increase the flow of coal through the feeder. The idea is to transport the coal to the burners as rapidly as possible. In some cases, increasing the flow rate through the feeder will eliminate air pockets and smother the fire. In other cases, the fire will simply move from the feeder to the pulverizer. Pulverizer fires can be caused in the manner we just described, or they can also result from too high a temperature inside the pulverizer, or from a spark produced by metal-to-metal contact inside the pulverizer. Regardless of how they're caused, pulverizer fires can create significant problems for the operator. A pulverizer is a closed piece of equipment that utilizes the close tolerances between its rollers and the bowl to crush the coal. Excessive heat from a fire in the pulverizer can cause these components to warp or crack. In extreme cases, if the coal in the pulverizer ignites rapidly enough, the pulverizer can explode. As with the other equipment fires we've discussed, the primary method of handling a pulverizer fire is to increase the flow of coal through the pulverizer. This gets the coal out of the pulverizer and to the burners as rapidly as possible. There is another piece of equipment in the plant that sometimes is prone to fires. That's the air preheater. On rare occasions, changes in normal operating conditions, an incomplete boiler purge, or even dead spots in the flue gas flow path through the air preheaters may allow combustibles to accumulate inside. In the event that one of these situations occurs, a fire may result. An operator can generally increase airflow through a burning air preheater and blow the fire out. For the most part, the equipment fires that we've discussed are contained within the equipment and do not normally represent an immediate danger to the operation of the plant. However, like any abnormal condition, an operator must carefully monitor the situation to make sure that it doesn't get worse. Now, just as it is necessary to understand the proper action to take in the event of an equipment fire, it's also necessary to understand what not to do. The fires that we've discussed occur inside closed equipment. In many cases, there are access doors on these pieces of equipment that allow maintenance to be performed. If an equipment fire is suspected, under no circumstances should an access door be opened. By leaving access doors closed, you increase the likelihood that the fire will consume all available oxygen and eventually smother itself. Opening an access door has exactly the opposite effect. An immediate supply of oxygen is made available for combustion, which could make the fire worse or even cause an explosion. Another thing you want to avoid is flooding the burning equipment with water. Bunkers, feeders, pulverizers, and air preheaters are all made of heavy metal. If a fire occurs, the temperature of the metal increases. If water is suddenly poured on the metal, it will cause the metal to cool rapidly, and this can create warping and cracking that will actually damage the equipment more than the fire could. In some cases, water can also make the fire worse. Fires in bunkers and coal piles generally occur deep down in the coal. Water has to filter through the chunks of coal to get to the fire. In doing so, the water can cut passageways for air that can actually feed the fire and increase combustion. In all cases, your plant will have specific procedures that you should follow when dealing with equipment fires. Throughout this program on abnormal and emergency conditions, we've looked at problems that happen only on rare occasions. It's important that an operator be prepared to handle these types of situations and have a thorough knowledge of the procedures which apply. The basic rules for dealing with any abnormal or emergency operating conditions are: identify the source of the problem, take immediate action to correct the problem, and return the unit to normal operation as quickly as circumstances and procedures will allow. Take some time now to finish reading the material in your text and answer the final set of questions. If you want more information on abnormal or emergency operation, ask your instructor to help you.